The other library which I can always make use of is what is the planning library or the motion planning library. So the input is the position of the robot, or let me say the pose of the robot. Position does not always imply angles. The map. So the map is globally available. So at least in simulation, it's globally available. So it needs a map. It needs the pose of the robot. So those were my two inputs, and the output is a trajectory. And to clarify, let me call it as the deliberative motion planning. So that's always available as a service. So you can do a function called always. The pose of the robot, take it from the localization system, give it to the motion planning library, take the map from the simulator, give it to the motion planning library, and thereafter you can get the trajectory as a straight away output. These are the things that you need even before you actually program the robot. These libraries should be up and existing. Now the problem is that if I am doing an actual robotic simulation, now if I'm doing an actual robotic simulation, then remember the beautiful picture that we painted all the way over here, which was my replica of the physical robot all the way up over here. Now that's the map as physically exists. We were people who did not have a lot of money, and therefore we were doing simulation. The robot does not know about its map, so I just dragged and dropped the robot. It's like opening from the package a new robot. In the simulation, everything is known, but in reality, the robot doesn't know anything. In reality, the robot doesn't know its position. In reality, the robot does not know its map. And because in reality, the robot absolutely doesn't know its map, so now I'll have to be very careful with two words. The first is what the simulator knows, which is everything, all maps, all positions, etc. And what the robot knows. Initially, nothing. And therefore what I do is I call a SLAM library and make a map. So far, if it was just a beautiful movie, the map is always known. And once I do that, I have what is called as a mapping server. The mapping server, it provides to the collision detection library the map as and when needed. Who uses the map? As of now, the collision detection library uses it. So the map was recursively stored in a space partitioning format, the octree format. So the mapping server does exactly that. It provides the collision detection library the map in the way that it uses it. Now there's one more library which is related. So mapping server, it takes the map as input from SLAM output and answers all map queries. Now another reference to the map was for the localization system. The most popular SLAM library is not gmapping, but it's one of the options. So what does localization do? It always tells the robot its own position. The simulator knows the actual robot position, but the physical robot that we just opened in the simulator, it doesn't know its position. Why? Because when I open a robot in my laboratory, the robot does not know its position. So that is what is the localization system. So the localization system, it takes all sensor readings and map as input and calculates robot pose. So that's why I need a localization system. Now everything was on a request response basis. You send a request for motion planning library, you make a function call, you'll get the response, you'll get the output. For localization, it's an information that should always be readily available. For mapping, it's an information that should always be available. And the localization system and the mapping system, of course, talk to each other. They both exchange information, ensuring location will always be available to your library, will always be given to the robot as per the best estimate. A library is running and calculating the position in the background. That's just like you navigating, and your satellite navigation system calculates your position and always lets you know. And the mapping server, which always ensures that the map as per SLAM output is always available to you, and you can query it as and when required. So these are the two services which are always running, and the output is always globally available. So if you want to use your position, you can use it as a normal variable. You can just use it as an information that is available with you, because in the background there are these services which are continuously updating the map and continuously updating the location of the robot. And that's exactly what we'll assume when we actually program the robot, that if things are absolutely available. Now we come to the actual programming part of it, and we come to the part where so far everything was either static. So a visual library will look at the beautiful picture which is right here. A visual library will look at this picture. I can drag and drop, I can add entities, I can add items. And dynamics ensures that it's always physically feasible as per physics rules. So no more cheating. And the graphics library ensure that all the information is available on your 2D computer screens. That's by using this virtual cameras. And there are lots of services and libraries which are actually running in parallel on a request response basis. Using that, I need to program maybe one, maybe multiple robots, and maybe other entities. So there could be a fan, which is what I see right in front of me. And this fan will always continue rotating. So of course there's a motor here, and you need to rotate the motor at a normal speed. So now what I have is that simulation using all these entities, simulation using all these entities that I've dragged and dropped will be done by using scripts, and therefore let us start doing it. So it's programming by scripts. So let's say script number 1 for fan. That's a simple script. Script number 2, what I already spoke about. So there's a code that must always calculate the robot position using onboard sensors, and that's something that should always be running. And because that should always be running, I should always have my own position at each and every point of time. So that's what I say as script number 2. That is a script that handles all the localization aspects of the system. So I need to control the robot. There's like this fan had a script for itself. The control also has a script for itself. So there's a script which keeps on moving the robot. It keeps on controlling the robot. So that's the same problem. It keeps on measuring the error by taking location from here and calculating whatever it needs to calculate as the error, derivative of it, integral of it, proportional, directly proportional for it, and it calculates whatever the v omega should be there, and it moves the motor. Now, this is what it's interesting, that there's a motor here, there's a motor here. All motors are actually operated by the dynamics engine or the physics-based engine. So the output is what is directly given to the simulator, which simulates it based on the dynamics engine property. So there's a constant torque that needs to be added in the free body diagram. So that constant torque is, external torque is added in the free body diagram using all this. And similarly, I'll have replanning or planning. So as of now, what we did not consider is that there is a robot which is over here. It wants to go over here and it continuously keeps on going around over here. And unfortunately, what happens is that it reaches here and suddenly it reaches here and suddenly it, oops. It reaches here and suddenly this gate gets closed. So now it needs to reroute. So there's a script running in parallel that always ensures that the robot's master trajectory is always correct. And that's exactly what your satellite navigation does. You take improper routes and then your satellite navigation is like, there is no way that you can reach your destination. The old route you did not take, you went on your own way, and now it gives you a new dynamic route. Sometimes you're going, somebody reports an accident, says this route is blocked, so the satellite navigation says, okay, let me calculate a new route for you. So that's replanning. Initially planning and thereafter replanning. And how will the script get to know that something has changed because of the mapping server? So the robot sensors will report this is closed. They'll report an unusual, not a dynamic human being, which was not a part of the static map. It'll report a blockage and the mapping server will actually block that up. So a lot of things are actually happening out there in the parallel, and that's when we have just taken in one robot. Now, inquisitive question would come is that can this be merged into one script? So I write a program like this, while forever, calculate position, calculate new plan, rectify plan, calculate, control input, and here of course update map. And the answer is, of course, no. So why is the answer no? So let's compare two scripts. The first one is just one script that does everything, and the other one is these four scripts. Now, calculation of the position is absolutely very fast, so it takes 0.08 seconds. Update of a map is little slow. Basically, there's a lot of global information that needs to be updated. This is the most problematic part, and controlling is very fast. So basically, this operates at 1 divided by 0.08 hertz. This operates as 1 divided by 0.2 hertz. This operates at 1 hertz, and this operates at 1000 hertz. Now, if you really go upon this thing is, so that means approximately you are applying one control input at every second. And imagine if this was what is done in the self-driving cars, the answers would be terrible. The answers would be absolutely terrible, because somebody would come in front of a self-driving car and it is calculating a new route, and till then it's moving by the same speed. So by the time it sees that there's someone, the accident would have already happened. You make one decision every second, and that's why you don't drink and drive, because your decisions, which are in a few milliseconds, they become in just under a second. When you are heavily drunk, in fact, they are more than a second. So the speed deteriorates. In fact, what is not mentioned over here is that how do you calculate your position? So you get LiDAR readings and you do vision, which is the image-based vision. So this one again could take in half a second, and this one is usually fast. So in every cycle like this, there will be one step which will be too much time taking. And because that will be too much time taking, you are not making control decisions at the rate that you could. And the answer to this thing is that, of course, everything needs to be as parallel as possible, so that different modules can work at the maximum frequency that is possible. And that's why we say that in robotics, every module works parallel. Because every module works at a different frequency. So let's take into example before I take this one specifically. So let's repeat the example of a self-driving car again. So that's my self-driving car. There's a LiDAR sensor over here, and there's a video camera over here. And there's a pedestrian who's crossing by. Now the video camera takes in half a second to process. This one processes 1.001 seconds. So in general, what happens as soon as the person comes, this in fractions and fractions of a second detects that there's something wrong, there's an obstacle right ahead of me. It either sends the emergency stop, the vehicle immediately stops, irrespective of everything, or it tells a control algorithm that the errors are terrible, the distance from the front obstacle is too small, so reduce the speed as quickly as possible to zero, and that's how emergency braking happens. Now, if you were calculating the route, 1 second the vehicle would have moved without control, because you're waiting for rerouting, you're waiting for computer vision algorithms, you're waiting for all the deep learning algorithms that are in this vehicle that do all the face recognition and everything. It's not a parallel architecture, it's a step-by-step architecture, and all this is taking 2 seconds. So 2 seconds the vehicle will move uncontrolled. Over here you realize that, okay, my vision sensor and ultrasonic both say, now you have both information that there's a person and I may collide, let's apply a brake, but what's the use? The accident already happened here. The dynamics library does not wait for anything. The dynamics library will tell you, okay, accident happened, and it will not let the vehicle move. The person would be already into a very bad shape. So You say that the emergency stop based on ultrasonics operates in parallel. So whenever the distance will be too less, it will send a direct emergency stop. Another example, that's the trajectory that my robot wants to make. And this trajectory is getting affected by some ensuring that the route is the same, which takes a long time. And there are some vision libraries which do some global consistency checks about my position or anything like that. So there's an inspection library, and as the robot is going, it's inspecting who all are the students who are sitting in their laboratory places and who are the students who are not at their places, that's empty seats. And my robot goes all the way up around over here. Now the problem is this inspection library, it does high precision face recognition that takes 1 second. So 1 second my robot moves uncontrollably, then it realizes that okay, the errors are too large, then it makes a correction over here, and then 1 second it moves uncontrollably, so it's actually hit the person. Then again it moves 1 second without control, while in reality the control algorithms that we saw, they can make the robot trace this trajectory because they operate at 1000 hertz or they operate at 0.001 seconds. So if you have a nice dexterous trajectory, you need to operate at 1000 hertz. You cannot trace this trajectory with 1 hertz or half a hertz. You need to operate at 1000 hertz. And therefore my control algorithms, because of the dexterity of this trajectory, need to operate as quickly as possible with whatever latest information is available about the position. It may not be perfect. The information about the map may not be perfect. It may have changed, but these are low frequency operations. When accident happens, you don't need to know immediately in milliseconds. You can wait up to a few seconds before rerouting. Similarly, for the inspection library, the person will be in your field of view for a long time, let's say 5 or 6 seconds. Even if you operate at half a hertz, that's okay, but your control has to be in 1000 hertz. And that's a big problem in robotics, that different modules, they operate at different frequency. In fact, why only different modules? So let's amplify that. Every sensor operates at a different frequency. The vision sensor, video cameras are the least. The ultrasonics are usually the highest. The LiDAR is very high. So the planning operates at a different frequency, just less than a hertz or sometimes a hertz. The reactive planning operates at a different frequency. The controller operates at a different frequency, which is one of the highest. And therefore you have everything is operating at a different frequency, and it's important. If you don't control at high frequency, you cannot take in dexterous trajectory. If you don't operate your sensors at high frequency, they don't let you emergency stop. The planning can be at very bad frequency, and the reactor planning could also go in 10 hertz. That's absolutely okay. You look at people, you don't need to continuously rectify your plan. You can rectify your plans once in a few milliseconds. And that's why I say that each one of these should be a parallel script